So I want to talk, or I want to give you a short overview about what we have done regarding evaluating the hazard potential in free collisions. So what we did in the Rossini project was we developed a conversion methodology which allows us to evaluate hazard potentials of coboards, and especially here in free collisions. So what we have right now is on the left side, we can distinguish between two contact types. So we distinguish between crushing, which means that the robot is pinching the human body part at high speed. And we also have the case impact, so meaning that we don't have any clamping. The body part is moved to free. We don't have any spatial constraints. Okay, so we don't want to, today I don't want to talk about pinching, so clamping, because this is a special type which is solved, so there are no need for any improvements. So what we see in the middle of the slide is a very simplified model for these kinds of contacts. So crushing means we have the robot which is moving with the mass against the body part which is affixed by an obstacle. Okay, and what we would receive for these states, so let's assume the robot has a velocity of 250 millimeters per second, and let's assume it has a weight of 15 kilograms. Then for the case of contact at the lower body, again, I guess it's a forearm. Here it's a forearm. You can assume a stiffness of 40 newtons per millimeter. We will receive the red curve seen here on the right, plotted here in this diagram. So, and for the free impact, so meaning that we don't have any special constraints here, drawn in blue at the bottom of the slide, we will observe a completely different contact force plotted over time, here depicted by the blue curve. So we have the same, exactly the same states from the robot, but just a different condition, and of course, and it's obvious we will receive a different force. And what we can see is that the force is reduced by 43%, and this directly translates into a robot speed which can be increased by 2.9 times, and then we still do not exceed the force we observe in crushing. So both contact types have a significant different dynamics. Okay, that's just as a background information. And now we come to an essential limitation. So when we are doing this measurement, we can only measure this case, so crushing. So even if you want to assess the transient case, we cannot do this today because this measurement device, which we can see here on the photograph, it must be affixed to a rigid structure in order to ensure that we have a certain repeatability and a certain accuracy. So you cannot hold it by hand because this will change the stiffness configuration. It will definitely very difficult to have to receive repeatable results. Okay, so again, what we want to assess is this one. Impact, so transient contact, but what we can measure is only crushing. So the case where the body part is restricted in terms of its motion by an obstacle. Okay, and the consequence is, of course, please keep in mind that we have a significant difference here in terms of the contact force and the speed, that we will receive, of course, lower speed than we should, lower speed than we could have when we have a real transient case. So the speeds are artificially reduced because we cannot measure it. Good. So this is the current state. And what we developed in the Rossini project was a conversion technique, actually. So again, we have these two contact types, transient and quasi-static. Okay. We have already seen this, and we can distinguish the transient part into crushing and impact. So we can measure the crushing contact, and what we want is we want to have a result for the impact, which we cannot measure. And here at this, so here this is exactly what we did in Rossini. So we developed a conversion technique which allows us to transform the results received from a crushing into the case which will, or into the forces which will reflect the impact case. And this comes, or this works, or this bases on 3 steps. So the first one is that we need to determine the effective robot mass and also the effective body mass. So the effective mass of the body part which is affected by the impact. Then we can calculate a reduction factor, which reduces the measured maximum force from the crushing case into the case that would reflect the impact. Okay, and what we need for that is here, keep in mind this model, we need to calculate, of course, the reduction factor. We need to calculate or determine the effective robot mass, and we also need to determine the effective mass of the human body. Good, this is the approach. And this is our solution. So we are here in the photograph. So we're doing this measurement. We receive a maximum, or we receive, or we measure a force over time. Okay. So here illustrated on the left side from the slide, and what we can do from, or what we can derive from the force signal is we can estimate very easily effective robot mass. This is, of course, not 100% precise, but it will give us a conservative estimation. So we overestimate the robot mass, which is good because this gives us a margin that is conservative and will not lead to an underestimation of the contact forces. Good, we have this. And what we need also is the effective body part mass. This is much more complex than this one here. So because the mass or the effective mass of the human body depends on the contact points, location, on the direction of the impact, and on the body posture. So here for that we need a model. And that's why we developed the Rossini human body model, which gives us exactly what we need, the effective mass for different body postures for different locations and so on, the force. Then we can very easily calculate this reduction factor. So we confirmed an experimental test with different cohorts that this factor allows us to precisely transfer the contact forces from a crushing case to an impact case. So by simply multiplying the maximum force by the reduction factor, and this will give us an equivalent impact force. Sorry, you cannot see the symbol here because it's drawn in white. So here should be an Fmax with a star. And the good thing is, this is, I would say, a huge success for the Rossini project. So this methodology will be also included in the ISO PAS 5672. This is an upcoming normative deliverable from ISO, which will set the requirements for doing these measuring, these tests, this collision tests with robots. And what's really an advantage for us is I'm the convener of this working group. So it's IC TC299 working group 8. And we are working currently on this project. And this was a good opportunity for us to bring this also in. And this was accepted so far, but it's not yet published. There is still a ballot which we need to take, but there is great potential that we will have it published by the end of September this year. Good. Back to the human body model. Just a brief overview. As you can see, it's a multi-body system with a lot of center of gravities, links, joints, and so on. And we use this model to calculate the effective mass of the human body model. Of course, we can use, or we can apply different body postures. We can apply different impact directions or different contact points and so on. The good thing here is that this model will be published, I hope soon, at the Python Lab, which will be then available as open source in GitLab. So everyone who's interested in using this model, you can download it, use it. But we still need to figure out which license model which license model we need for this kind of open source. Good, and just a brief overview of the potential. So this curve is very easily to read. So here we have the impact velocity taken from measurements with real collaborative robots. Here on the right side, on the y-axis, we have these. Actually, the left side, we have the maximum impact force and measured with a pressure force measurement device. And what we obtained from the test is the green curve with a fixed device. So the green curve represents exactly what we will receive today because we need to fix it. And then we did some test with the movable device. So we will receive the red one if the device has a weight of approximately 23 kilogram, and for 7 kilogram it's the blue curve. And what you already can see here is that we will observe a significant increase or decrease of the forces, increase in velocity if we make the PFMD movable. But movable means more effort, which needs to be put into these measurements. That's why we want to go with our conversion technique. And here we compare the results to our conversion technique. So again, we have the green curve taken with the fixed measurement device, and with our conversion technique, we will receive the red curve, which will give us, at least for this case, for this condition, an increase of 26% in velocity compared to the 32, which we will receive with the movable device. So we are a little bit below what is actually achievable with a movable device. So here, this shows us that we are underestimating the speed. So we are on the conservative side, which is good. And for the blue curve, which is 7 kilogram, we will receive an increase of 73% compared to 100%. It's approximately the same relative difference. So in short, in summary, the conversion technique will allow us to go even faster when we can ensure that we have transient contact. That's everything from my side. And yeah, if you have questions, then please, I hope that we have time after the presentations to answer them. Thanks.